Taylor polynomials and approximations. Polynomial functions can be used to approximate other elementary functions such as sine of x, e to the x, cosine of x, and natural log of x. On your calculator, graph y1 equals sine of x, and then the polynomial approximation, which would be x minus x to the third over 3 factorial plus x to the fifth over 5 factorial, and we could keep going with that with minus x to the seventh over 7 factorial, but let's just stop at x to the fifth. So I've already have these plugged in, and notice when we graph these, here's the wave of sine of x, and in the polynomial it's an x to the fifth, and it follows sine very closely for about one wave. And the more we add on to this, the more closely and the longer it will follow the polynomial. Definition of an nth degree Taylor polynomial. If f has n derivatives at x equals c, then the polynomial p sub n of x equals, we have f of c, first derivative, second derivative, third derivative, and so on. And notice it goes over 0 factorial, 1 factorial, 2 factorial, 3 factorial. And it's also x minus c to the 0, x minus c to the first, x minus c to the second, and so on. So we have this nice pattern with the Taylor polynomial. That's called the nth degree Taylor polynomial for f at c, named after Brooke Taylor, an English mathematician. If c equals 0, then it's the same polynomial. It's centered at 0. That's called an nth degree Maclaurin polynomial, and it's named after the English mathematician Colin Maclaurin. Find the Maclaurin polynomial of degree n equals 4 for f of x equals e to the 4x. Well, we're going to start out by finding f of 0, which the function is e to the 4x. And that's just going to be e to the 0, which is 1. And then we have the first derivative is equal to 4 e to the 4x. And that, when we plug 0 in, we're just going to get 4 times 1, which is 4. And then the second derivative at 0 is equal to 16 e to the 4x. And when we plug 0 in, we get times 1 again. That's going to be 16. The third derivative at 0 is now 64 e to the 4x. And when we plug 0 in, we're going to get 1 again, so we get 64. And then finally, the fourth derivative at 0 is, let's see, 16, 1, carry the 1, 256 e to the 4x. And so that'll be 256. Well, now the Taylor or the Maclaurin polynomial centered at 0 is going to be, first of all, 1, and then plus 4 over, that'd be over 0 factorial. I guess this would be over 1 factorial, times x minus 0, which is just x, and then plus 16 over 2 factorial, and then times x squared, and then plus 64 over 3 factorial times x to the third, and then finally 256 over 4 factorial times x to the fourth. Example, find the Maclaurin polynomial of degree n equals 6 for f of x equals cosine of x. Then use p sub 6 of x to approximate the value of cosine of 0.1. So we want to go all the way to n equals 6. Well, let's get f of 0 because we're doing Maclaurin. Now that's cosine of x, and cosine of 0 is 1. And then first derivative is equal to negative sine of x, and that's 0. And second derivative is equal to negative cosine of x, and that's going to be equal to negative 1. Third derivative is going to be sine of x, and that's 0. And then fourth derivative is going to be cosine of x, and cosine of 0 is 1. And then fifth is negative sine of x, which is 0. And then finally the sixth derivative is negative cosine of x, which is negative 1. And notice the pattern goes 1, 0, negative 1, 0, 1, 0, negative 1. So when we write the polynomial, p sub 6 centered at 0, that's going to be, first of all, we have 1. And then we actually have plus 0. We would have this. We'd have plus 0 over, well, not over, it's over 1 factorial, but then times x, and then we'll have minus 1 over 2 factorial times x squared, and then we'll have the plus 0 over 3 factorial times x to the third, so that's going to be gone. So the odds are all gone. And then we have, we'll have plus, because now we're here at the fourth derivative. We'll have 1 over 4 factorial, and then x to the fourth, and then plus 0 over x to the fifth, over 5 factorial, actually, 5 factorial, x to the fifth, and finally, we have minus 1 over 6 factorial x to the sixth. So now if we remove all those zeros, we have an x to the 0. So we have 1, and then we have minus x squared over 2 factorial, and then plus x to the fourth over 4 factorial, and then minus x to the sixth over 6 factorial. And that's the pattern for cosine of x. Now remember that cosine of x is an even function, and that's how we remember that it has all of the even powers. And the only thing you really have to remember other than that is that the signs are going to alternate, plus, minus, and it'll start with a plus. So even function, even trig function, even powers. Now we're going to use that to approximate p sub 6 of 0.1. So we'll have 1 minus 0.1 squared over 2 factorial plus 0.1 to the fourth over 4 factorial, and then minus 0.1 to the sixth over 6 factorial. And I'm going to stop this and I'm going to enter that into the calculator. So we entered this into the calculator, we press enter, and we get 0.995. So that's equal to 0.995. Well, let's see what we would get if we actually took the, let's see, we're doing cosine of 0.1, and we get something very, very close. It's very accurate. Example, find the Taylor polynomial of degree n equals 6 for f of x equals natural log of x at c equals 1. Then use p sub 6 of x to approximate the value of natural log of 1.1. So I've kind of fast forward here. F of 1 equals the natural log of x, that's the function, and natural log of 1 is 0. Then the first derivative of natural log of x is 1 over x. That's really x to the negative 1, and when we plug in 1, we get 1. Then we do the next derivative, and we get negative 1. The next derivative, we get 2. Then we get negative 6 on the next derivative, just using the power rule for derivatives. And then we get 24, and finally we get negative 120 when we plug 1s in for all of these x's. It's just going to be divided by 1. So now the polynomial sub 6 of x centered at 1 is going to be equal to, the first one is 0, so we have 0, and then plus 1, so that's going to be 1 times x minus 1, and really over 1 factorial. And then we have minus 1 times x minus 1 over 2 factorial, but to the second power, plus 2 times x minus 1 to the third over 3 factorial. And then we get to minus 6 times x minus 1 to the fourth over 4 factorial. And then we have plus 24 times x minus 1 to the fifth over 5 factorial. And finally, minus 120 x minus 1 to the sixth over 6 factorial. And that's the polynomial. And we are asked to approximate natural log of 1.1. So I'm going to plug that into the calculator. So I've stored 1.1 into x so that I don't have to type 1.1 every time. I can just type x. So I have it all typed out. We press enter and we get 0.095. So the approximation is 0.095. Let's find out what the natural log of 1.1 is. So we have natural log of 1.1. It should be a pretty close approximation. We press enter and we get out to 1, 2, 3, 4, 5, 6, 7. About it's accurate to about 6 or 7 decimal places. Suppose that g is a function which has continuous derivatives, and that g of 2 is 3, g prime of 2 is negative 4, g prime double prime of 2 is 7, and the third derivative at 2 is negative 5. Write the Taylor polynomial of degree 3 for g centered at 2. So the polynomial, we're looking at third degree of x centered at 2 is equal to 3, and then we have minus 4, and that's going to be x minus 2. Now that's over 0 factorial, that's over 1 factorial, which both happen to be 1. Then we have plus 7 times x minus 2 squared, and that's over 2 factorial, and then minus 5 times x minus 2 to the third over 3 factorial. Use the Taylor approximation that e to the x is 1 plus x plus x squared over 2 factorial, x to the third over 3 factorial, for x near 0 to find the limit as n approaches 0 of e to the x minus 1 over 2 to the x. So we have the limit as n approaches 0, and we're going to use the approximation for e. So we have 1 plus x squared over 2 factorial plus x to the third over 3 factorial, and we have minus 1 on the end here, and that's all over 2x. And that is equal to the limit as this should be x approaches 0, not n. We have 1 minus 1, that's 0. And so let's write that, x plus x squared over 2 factorial plus x to the third over 3 factorial. So the 1 minus 1 is 0. And then we have the limit as x approaches 0 of, now we can cancel an x out of all of these. So that's going to be 1 plus x over 2 factorial plus x squared over 3 factorial over just 2. And when we plug the zeros in, that becomes 0, that becomes 0. So the answer is 1/2. Example, given that p sub 2 of x equals a plus bx plus cx squared is the second degree Taylor polynomial for f about x equals 0, what can you say about the signs of a, b, and c if f has the graph pictured at the right? Justify your answers. All right, so if we have p sub 2 of 0, let's say we plug 0 in. We're going to pick an x value of 0. That's equal to a plus b times 0 plus c times 0 squared, which is equal to a. Now, a is the y-coordinate at 0, and the y-coordinate is up here, and it's positive. So a is positive. We can say that. Then, if we take the first derivative, that's equal to, well, that's going to be 0, and then we have b, the derivative of bx is b, plus 2cx. Now, if we're looking at 0, then we plug 0 in, we just get b. Now, the slope, the first derivative, represents slope of the tangent line, so the slope of the tangent line is positive. So b is also positive because the slope of the tangent line at 0 is positive. Then the second derivative at 0 is equal to, and now we take the derivative of this, the derivative of b is 0, and the derivative of 2cx is 2c. And now this is the second derivative, so this is concavity, and we see that at 0 this graph is concave down, so c is negative.